Hello everyone, I'm Dr. Aris, and today we're embarking on a journey to rethink one of the most familiar experiences in our lives. We are going beyond Newton's classical view of gravity to explore a much more elegant and profound reality. For centuries, Newton's perspective dominated. He taught us to think of gravity as a force, an invisible, instantaneous pull between two masses across a void of empty space. This famous inverse square law allows us to calculate planetary orbits with incredible precision. However, it treats space and time as a static, unchanging background where forces just happen. Then came Einstein, who offered a radical paradigm shift. He realized that gravity isn't a force acting times within time-space, but rather the result of the times-geometry times of space itself. These field equations summarize the core of general relativity. Mass and energy tell space-time how to curve, and that curvature tells mass how to move. There is no invisible rope pulling us. We are simply following the curves of the universe. The breakthrough was the equivalence principle, the realization that being accelerated in a rocket feels exactly the same as standing in a gravitational field. This link between movement and gravity is what led us to geometry. Since we just established that gravity is linked to movement and geometry, we need a stage where this geometry can unfold. We call this stage the fabric of spacetime. Think of it this way: instead of viewing time as a separate clock ticking away in the background, we must treat it as the fourth physical dimension. It's inextricably woven with the three dimensions of space we move through every day. To visualize this, we look at a four-dimensional coordinate system. Imagine adding a time axis to our standard length, width, and height. Notice this T label here. In this framework, an event isn't just a location, it's a specific where and a specific when. Everything in our universe is a point within this vast 4D fabric. This formula represents the invariant interval. While distances in space or durations of time might look different to different observers, this specific combination remains the same for everyone. It is the fundamental ruler of Minkowski space. So, keep this image in your mind: a unified, four-dimensional grid that permeates the entire universe. Now that we understand the stage, let's look at how mass begins to warp its very shape. Building on that concept of the four-dimensional grid we just established, we've reached a pivotal moment in the course. We're moving from the where to the why with the geometry of mass. You see, matter doesn't just sit passively inside space, it interacts with it. Think of spacetime as a physical fabric like a trampoline where mass acts like a heavy bowling ball, physically warping and curving the surface around it. This beautiful relationship is perfectly captured in the Einstein field equation. While it looks complex, it essentially tells a simple story about the universe's structure. The left side represents the geometry, the shape and curvature of space, while the right side represents the matter and energy within it. In Einstein's words, matter tells spacetime how to curve, and spacetime tells matter how to move. To help you visualize this better, let's watch a simulation of how a massive object creates a well in the spacetime grid, pulling everything toward its center. Notice how the curvature is most extreme nearest to the mass. This is why larger objects cause deeper distortions. Next, we're going to dive into an interactive gravity well to see how these curves dictate the motion of planets. Welcome to the Spacetime Simulator. Let's explore how mass shapes the very fabric of our universe. Use this slider to change the central mass. Notice how the grid lines bend as the value increases. At maximum mass, we create a deep gravitational well. This curvature represents what we perceive as gravity. Now, let's look at the orbital velocity. This determines how a particle moves through this curved space. With a balanced mass and velocity, the particle follows a geodesic, the straightest possible path through this curved geometry, resulting in a stable orbit. Remember, mass tells spacetime how to curve, and spacetime tells matter how to move. Try lowering the velocity to see the particle fall into the mass. Building on our interactive exploration of the gravity well, we now arrive at a fundamental concept: geodesics. This is the secret to understanding how objects know how to move through space. A geodesic is defined as the shortest possible path between 2 points. In our everyday flat world, we simply call this a straight line. On a flat surface, that path is simple and familiar, but once we introduce the mass we just talked about on the previous page, things get interesting. In curved geometry, the straightest path follows the intrinsic curves of the surface. To an outside observer, this path looks curved, but for the object traveling it, it's the most direct route possible. This brings us to the core of Einstein's vision. Free-falling objects aren't being pulled by a force. They are simply traveling in straight lines geodesics through a spacetime that is itself curved. Consider the moon. We see it circling the Earth and think of it as a closed loop. But if you look at it through the lens of general relativity, the moon is actually moving in a straight line through the curved geometry created by the Earth's mass. Now that we've explored how mass curves the geometry of space, we must address the other half of the space-time coin. As we see here, time is curved too. It isn't just a background stage, it's a flexible part of the cosmic fabric. In Einstein's universe, mass doesn't just warp the 3 dimensions you can walk through, it warps the geometry of time itself. This curvature is what links the spatial paths we just discussed to the actual speed of light. This warping leads to what we call gravitational time dilation. The rule is simple but profound. Clocks run slower in stronger gravitational fields. If you are closer to a massive object, your seconds actually last longer than those of someone in deep space. Think back to the movie Interstellar. This effect is why time passes relative to your gravitational position. It's not an optical illusion or a mechanical error in the clock. It is a fundamental change in the flow of time. To calculate this exactly, we use this formula. It shows that as the mass m increases or the distance r decreases, the proper time experienced at that location t0 slows down relative to a faraway observer. It's the mathematical heart of relativity. Now that we've explored the mathematical heart of relativity and how time slows down near mass, you might be wondering, where is the proof? These aren't just abstract ideas. They have been confirmed by rigorous observation and are even essential for our modern technology. The first major breakthrough happened in 1919. During a solar eclipse, astronomers observed light from distant stars bending as it passed the sun. This confirmed that massive objects warp the geometry of space, forcing light to follow a curved path. But we don't have to look to the stars for evidence. We use it every day with GPS satellites. These satellites are orbiting far above the Earth, where the gravitational pull is slightly weaker than what we feel here on the surface. As we just covered on the previous page, weaker gravity means clocks actually tick faster. For a GPS to work, we have to synchronize these satellite clocks with ours on the ground to an incredible level of precision. Look at this table showing the discrepancy. If we didn't account for general relativity, the timing error would cause GPS locations to drift by several kilometers in just a single day. It's the ultimate proof that the curved time we've been discussing is a physical reality. Now that we've seen how mass curves time and space in our own solar system, let's push these equations to their absolute limit. We are entering the realm of the most extreme objects in the universe, black holes. Every black hole is defined by its event horizon. As we discussed when looking at geodesics, light follows the curvature of space. Here, the curvature is so intense that light itself cannot escape. It is effectively the point of no return. Once an object crosses this threshold, the escape velocity required to get back out is greater than the speed of light, which, as we know, is the universal speed limit. We can actually calculate the size of this horizon using the Schwarzschild radius formula shown here. It tells us that any mass, if compressed enough, can become a black hole if it reaches this critical radius. But what lies at the very center? The singularity. This is where the fabric of space-time we've been visualizing doesn't just curve, it tears. At the singularity, curvature becomes infinite and our current laws of physics begin to break down. It represents the ultimate mystery, a place where density becomes infinite and the geometry of the universe as we know it ceases to exist. Before we move to our final summary, let's think about what this means for our understanding of reality. To wrap up our journey today, let's bring everything together into what physicist John Wheeler famously described as the cosmic dance. We have moved far beyond Newton's simple pull to a much more elegant reality. First, we have matter. Whether it's a star, a planet, or even you and me, the presence of mass is the primary actor in this play. As we discussed when looking at those gravity wells earlier, matter tells space how to curve. It literally warps the environment around it. Then there's the other side of the partnership, space itself. It isn't just an empty stage, it is a dynamic participant. That curved space, in turn, tells matter how to move. Objects follow the natural contours of spacetime, traveling along those geodesics we explored in the middle of our session. The ultimate takeaway is this. Gravity is not a phantom force reaching across the void. Gravity is the geometry of the universe. From the precision of our GPS satellites to the shadows of black holes, this single concept explains the structure of our reality. Thank you for your brilliant questions today. I hope you look at the stars a little differently tonight.